Welcome. PSM 201 Studies Section 7 Inferential Statistics. Introduction. Statistical inference makes proposition about a population using data drawn from the population with some form of sampling, giving a hypothesis about a population for which we wish to draw inferences. Statistical inferences consist of, firstly, selecting a statistical model of the process that generates the data, and secondly, deducing propositions from the model. In this studies section, you will be introduced to inferential statistics and its classification. You will also learn about tests of association, applying chi-square test, and comparison of two population means using student t-test. Learning outcome. Learning outcome of studies section 7. At the end of this studies section, you should be able to define inferential statistics, explain estimation of parameter, discuss the theory of hypothesis testing, explain test of association, applying chi-square test, explain comparison of two population means using student t-test. Inferential statistics. The procedure by which we reach a conclusion about a population on the basis of the information contained in a sample drawn from that population is regarded as inferential statistics. Statistical inference procedures are employed to draw inferences about the population. Of course, the process of inference, that is generalization, based upon a relative few, is most accurate when the subpopulation, that is sample being studied, is 1. Homogeneous, that is uniform in character, 2. Truly representative, that is correctly reflect the larger group, and 3. Randomly selected to eliminate sampling error or bias. Depending on the research objective, we can classify statistical inferences into two categories, namely estimation and hypothesis testing. Estimation is a form of inferential statistics in which researchers want to estimate the value of a parameter. Example, the response rate of a leukemia investigative drug. On the other hand, hypothesis testing is another form of statistical inference where we want to compare the parameters for two subpopulations using statistical tests of significance, e.g., testing whether men have higher cholesterol level on average than women. 2. Estimation. A major purpose or objective of health research is to estimate certain population characteristics or phenomena. These characteristics or phenomenon can be quantitative, such as average systolic blood pressure of adult men, or qualitative, such as proportion with under 5 malnutrition. Recall that the sample mean X bar and standard deviation S are used to estimate the population mean mu and standard deviation sigma. The sample mean is not likely to be exactly equal to the population mean, and different samples would always give a different estimate due to sampling variation emanating from the fact that the results from either individuals vary or results from different samples vary. Thus, through population parameters difficult to measure, hence reliance on the sample data, we can have point or interval estimates. A point estimate is a single numerical value used to estimate the corresponding population parameter. For example, the sample mean is a point estimate for the population mean, and the sample proportion is a point estimate for the population proportion. However, having access to the data of a sample and knowledge of statistical theory, we can do more than just providing a point estimate. Hence, the interval estimate, known as confidence interval, which is the art of estimate in statistical inference, will be discussed in these units. sampling distributions. Population refers to the totality of all available units in a defined area or within the scope of interest to a researcher. The units may be individuals, households, families, schools, communities, insects, animals, and so on. On the other hand, sample is a fractional part or subset of the population selected for a study. Sometimes, selection of sample is the only visible way of studying a population. Other reasons for sampling is limited resources, which could be in terms of time, person, financial, and material. The distribution of values of a statistic obtained from repeated sample of the same size from a given population is called the sampling distribution of that statistic. The sampling distribution can be computed for the mean, median, standard deviation, proportion, and any other statistic. E.g., sampling distribution of mean is x bar approximately n into brackets Newman, s over square root of n. Central limit theorem. The central limit theorem is one of the most important ideas in statistics. The theorem provides us with a way to make inference from sample of non-normal populations. It states that given any population, and it does not matter whether or not it is normal distribution, as the sample size increases, the sampling distribution of the means approaches a normal distribution. It is a powerful theorem because it allows us to assume that given a large enough sample, the sampling distribution will be normally distributed. The central limit theorem describes the properties of sampling distributions. The mean of the sampling distribution is equal to the true population mean, implying that the mean of sample means is an unbiased estimate of the true population mean. On the other hand, the standard deviation of sampling distribution is directly proportional to the population standard deviation and inversely proportional to the square root of the sample size. This is referred to as standard error of the statistic. Standard error. Usually, total population of interest is larger than available resources, which oftentimes results in inevitable use of a sample. This, in turn, leads to the general subject of standard error. It is a statistic measuring the reliability of precision of an estimate. This is used to describe the variability of sample statistics by giving information on how far or close we were from estimating the true unknown parameter. Value of standard error is subject to the variability of individual observations and the sample size. The larger the sample size, the less the error in its estimates. Standard error, therefore, is expressed as the ratio of the standard deviation to the square root of the sample size. Standard error of the mean. Statistical expression of standard error of mean is given as A. SE S bar equals to S over square root of n for one sample, where S is the standard deviation and n is the sample size. B. SE S bar 1 minus S bar 2 equals to square root of S1 squared over N1 plus S2 squared over N2 for two independent samples, where S1 and S2 are the standard deviations of the group and N1 and N2 are the sample sizes in each group. Standard error of the proportion. Statistical expression of standard error of proportion is given as A. SE into bracket P equals to square root of P into bracket L minus P over N for one sample, where P is the proportion with the characteristic in the population and N is the size of the sample. B. SE into bracket P1 minus P2 equals to square root of P1 into bracket L minus P1 over N1 plus P2 into bracket L minus P2 over N2 for two independent samples, where P1 and P2 are the proportions and N1 and N2 are the sample sizes for group 1 and 2 respectively. Interpretation. A small variance for a sampling distribution indicates that most possible values for the statistic are close to each other, so that a particular value is more likely to be reproduced. In other words, the variance of a sampling distribution of a statistic can be used as a measure of precision or reproducibility of that statistic. In that, the smaller this quantity, the better the statistic as an estimate of the corresponding parameter. The square root of the sampling distribution variance is called the standard error of the statistic. In essence, standard error and standard deviation are the same quantity. However, the term standard deviation is used for individual measurements by describing the variability in the individual observation in a single population sample, and the term standard error refers to the standard deviation of the statistic. Confidence interval. Instead of giving just a value estimate of a variable, a confidence interval gives a range of likely values for it. This is useful because sample results will vary from sample to sample, so a range of values is better than a one-number estimate. A process whereby the point estimate and the standard error are combined to form an interval estimate is known as confidence interval. It is a range of likely values for an unknown population parameter at a given confidence level, which provide bounds, lower and upper, to our estimate of population parameters. On account of sampling error, it provides uncertainty attached to sample estimates. It is important to note that increase in sample sizes reduces standard error and confidence interval. By convention, the 95% confidence value is commonly used and expressed as 95% chlorine, that is statistic plus or minus 1.96 SE statistic. 95% confidence interval interpretation, where 100 random samples of size n taken from the same population and 95% confidence interval computed using each of these 100 samples. 95 of the 100 intervals will contain the value of true mean, Newman, within the endpoint. It could also be interpreted as the 95% chlorine will not include the true population value 5% of the time on the average. Advantages of confidence interval. Tell us by how much an exposure affects the subject. Focus is on range of values to be considered plausible for the population. Convey information on the magnitude of the differences in, say, blood glucose level between diabetic and non-diabetic patients. Give estimate of differences in, say, glucose levels that would have been obtained if total population were studied. Given confidence interval shows ability to dictate lack of precision of estimates. Ability to dictate significant and non-statistical significant effects or difference in that for comparison of mean values or proportion. Confidence interval containing 0 implies data is consistent with null hypothesis, which is said to be statistically significant. For relative risk or odds ratio, confidence interval containing 1 implies risk factor not statistically significant. Example: the mean diastolic blood pressure from 16 subjects is 90.0 mm mercury and the standard deviation is 14 mm mercury. 1. Calculate its standard error. Answer: standard error of mean is equal to S over square root of n, which is equal to 3.5. 2. Compute 95% confidence limit. Answer: 95% confidence limit is equal to S bar plus or minus 1.96 times x over square root of n, which is equal to 83.14, 96.86. In a bid to estimate the average number of heartbeats per minute for a certain population with a known SD, which is equal to 10. The average heartbeat for a sample of 49 subjects was found to be 90. Assume the 49 subjects were randomly drawn from a normal distributed population. Construct a 95% chlorine and interpret the results. Answer: 95% confidence limit is equal to S bar plus 1.96 times x over square root of n, which is equal to 87.2 92.8. Theory of hypothesis testing. Hypothesis is a conjecture about the characteristic or phenomena of a population that has not been verified. For instance, an endocrinologist may say NIDDM patients are generally younger than IDDM patients, and the truth of this could only come out after investigation. Meanwhile, the process of evaluating the truth of a hypothesis is referred to as test of significance or hypothesis testing. The process of hypothesis testing is a way of decision making. Most hypotheses involve investigating either difference between groups, e.g., the contraceptive prevalence rate between rural and urban communities, age at sexual debut between girls of high socioeconomic and low socioeconomic class, means CD4 counts between HIV patients and HIV patients with TB co-infection. Association between variables, e.g., the association between educational status and intravenous drug use, the association between income and drug adherence, association between number of clinic visits and morbidity. The 6 basic steps in carrying out the test of any statistical hypothesis are therefore outlined below. 1. State the null hypothesis, H0. 2. State the alternative hypothesis, H1. 3. State the level of significance, alpha. 4. Choose the appropriate test statistic. 5. Evaluate the test statistic. 6. Decision making. Type of hypothesis. Statistical hypotheses are stated in such a way that they may be evaluated by appropriate statistical techniques. There are 2 types of hypothesis testing, namely null and alternative hypothesis. 1. Null hypothesis, H0. Null hypothesis, usually denoted by H0, is a statement that forms the basis of investigation in a significance or hypothesis testing. It is a statement that does not prejudge the phenomenon of interest, and it is usually a statement of no difference, no effect, and equality. It is either rejected or not rejected. Some examples are: there is no difference in ARV adherence rates between male and females. There is no relationship between maternal smoking and low birth weight babies. Alternative hypothesis, H1. Alternative hypothesis is often represented by H1. It is a hypothesis formulated as an alternative to the null hypothesis, which the investigator will accept if the null hypothesis is rejected. It is usually the same as a research question or hypothesis, which we neither reject nor accept, H1. By convention, it specifies what forms of departure from the null hypothesis are of potential concern. This statement of inequality could either be stated or directional, one-tailed test, or non-directional, two-tailed test statements. An example would be that there is a difference in ARV adherence rates between males and females. Errors in decision making. There are 2 possible ways of committing error in hypothesis testing. These errors are referred to as type 1 and type 2 errors. Type 1 error. This is the error committed when the null hypothesis is rejected, when in actual fact it is true. The probability of committing type 1 error is usually denoted by alpha. By tradition, it is ideal to keep the chance of making a mistake when the H0 is true and only reject if the sample result is unlikely. The unlikeliness threshold is determined by alpha level, known as level of significance. Level of significance is therefore referred to as the pre-specified maximum probability of committing type 1 error, which is usually pre-specified as alpha is equal to 0.05. Type 2 error. This is the error committed when we fail to reject the null hypothesis, when in actual fact it is false, and the probability of committing type 2 error is usually denoted by beta. On the other hand, the ability or likelihood to rightly reject the null hypothesis is called the power of a test, and it is commonly expressed as L minus beta. Probability value, p-value. Probability value, known as p-value, is a measure of how much evidence we have against the null hypothesis. It measures consistency by finding probability of observing the results from a sample with results more extreme. Assuming H0 is true, smaller p-value implies greater consistency. That is, the smaller the p-value, the more evidence we have against H0 and vice versa. If the p-value is less than some predetermined cutoff value, e.g. 0.05, the result is said to be statistically significant. Interpretation: p-value is equal to 0.03. The following are the possible interpretation of p-value is equal to 0.03. If the null hypothesis were true, the probability of seeing something as or more extreme than we saw is the 0.03. There is a less than 3% chance of seeing something this or more extreme if the two groups truly have the same means. The result is said to be statistically significant since the p-value is less than some predetermined cutoff alpha is equal to 0.05. Types of statistical tests. Test statistic is a particular form of data summary to be used in an hypothesis testing. There are two basic types of statistical tests, namely parametric and non-parametric tests. Parametric tests. Statistical tests that assume the distribution forms for the measurement and parameters in the population are called parametric tests. Normality assumption is the commonest requirement for application of parametric tests used for statistical inference. Examples of parametric tests include, but not limited to, the following: Z-test for comparing two proportions, T-test for comparing mean value between two groups, F-test ANOVA for comparing mean values between several more than two groups. Pearson correlation, test for investigating the relationship between two quantitative continuous variables, non-parametric tests. The statistical tests that do not specify any assumption about the forms of distribution of the population parameters are referred to as non-parametric tests. Sometimes they are called distribution-free statistical method. In cases where data satisfy the parametric assumptions, non-parametric tests are weaker than parametric tests. Some common examples of non-parametric tests are sign test, Wilcoxon sign rank test, Mann-Whitney test, chi-square test, Kruskal-Wallis one-way ANOVA test, and Spearman rank correlation test. Choice of test statistic. Test statistic is computed from the sample data to facilitate decision-making on comparison tests. Thereafter, the probability of such statistic value, p-value, is compared with alpha level so as to reject or fail to reject H0. The choice of the test statistic is thus mostly predicated on the following: Study objective, estimation, comparison. Study design, independent or dependent sample. Type of variable or data, quantitative or qualitative. Sample size and sampling method, random or not. In summary, the following test statistic will be appropriate, bearing in mind the following consideration. Relationship between one qualitative and one quantitative variable can be reduced to mean difference between groups. If two group t-test, if more than two group f-test, true and over. Relationship between two qualitative variables. Z-test for difference in proportion. Chi-square test for association or independence. Relationship between two quantitative variables. Correlation analysis, strength of relationship. Linear regression analysis, prediction of one variable from the other. Comparison of two population means using student t-test. Student t-test, simply called t-test, is a parametric test statistic used to compare the difference between population mean values where sigma, population standard deviation, is unknown. It can be approximated by standard normal z-test when the sample size greater than 30. Other important assumptions include: 1. The outcome, dependent variable, must exhibit an underlying normal distribution. 2. The observation must be independent. 3. The equality of variances in the two groups. Student t distribution has more areas at the tails of the distribution compared with the normal distribution. This is based on degrees of freedom to take care of small sample size less than 30. The distribution is widely used in biomedical sciences. The various forms of t-test are one sample t-test, dependent two sample t-test, and independent two sample t-test. One sample t-test. This is the appropriate significant test for comparing a population mean with a hypothetical value. Researchers may want to determine if a particular sample mean is significantly different, larger or smaller than a standard value. Example: if it is previously known that the average diastolic BP in the population is 75 mmHg and a nursing officer is interested in testing whether the mean diastolic BP in recent sample is not 75 mmHg. The mean diastolic blood pressure from 16 subjects is 90.0 mmHg and the standard deviation is 14 mmHg. Solution: the hypothesis: H0, Newman is equal to 75 versus H1, Newman is not equal to 75. Level of significance: alpha is equal to 0.05. Test statistic: one sample t-test with 15 into bracket n minus 1 degree of freedom. Computation: t is equal to square root of n into bracket s bar minus Newman over s, which is equal to square root of 16 into bracket 90 minus 75 over 14 is equal to 4.2857 with the p-value less than 0.01. Decision rule: reject null hypothesis if p-value is less than alpha. Otherwise, do not reject. Decision or conclusion: H0 is rejected in conclusion that the average diastolic BP is significantly different from 75 mmHg. Paired t-test. This is used when the two samples are dependent or related. It applies to cases where each subject or member of a group is observed twice, e.g., measurements before and after certain interventions. Each subject or person is serving as his or her own control may also represent measurements on different people who are chosen on an individual basis using matching criteria such as age and sex. The use of paired t-test focuses on the difference in the measurements between the individual pair of observations in which the difference is treated as an individual variable, that is, reduced to a test of one population mean. Independent two-sample t-test. A common problem in statistical inference is a comparison of two population means using data from two independent samples, such that data points in one sample are unrelated to the data points in the second sample. The sample sizes may or may not be equal. We have two sets of continuous measurements, one of size N1 and one of size N2. In the above stated situation, the appropriate test statistic is the use of independent two-sample t-test for simplicity's sake. The assumption of unequal variance will be used in computing the standard error of the difference in order to obtain the estimate of the test statistic. Test of association applying chi-square test. Chi-square test statistic is an inferential statistic technique designed to test for significance relationship between two categorical variables, usually organized in a contingency table. In other words, it is the choice of test statistics to investigate the significance of association between two qualitative variables, e.g., association between gender and educational attainment. It is one of the non-parametric tests because it requires no assumption about the shape of the population distribution from which a sample is drawn. It can be applied to nominal or ordinal measured variable and is commonly applied to frequency and count data. Definitions. Chi-square test statistic is based on the discrepancy or disagreement between the observed data and what is expected if H0 is true. Often denoted by the quantity lambda square, it measures the extent to which, in a given situation, pairs of observed and expected frequencies agree. This is statistically expressed as lambda square is equal to summation observed minus expected square over expected, with degree of freedom equals to rows minus 1 times column minus 1. Theoretically, the test determines whether the deviation between observed and expected are too large to be attributed to chance. The lambda square statistic is calculated under the assumption of no association. Contingency table. Categorical data may be displayed in contingency tables. These apply when investigating association between two qualitative category variables, e.g., gender and drug compliance, also called a cross-tabulation. The table classifies subjects into different categories based on the different combination of the variables involved, e.g., in the former example, there are 4 category compliant males, compliant female, non-compliant males, and non-compliant females. Procedures. Compare the observed count in each table cell to the count which would be expected under the assumption of no association between the row and column classification. That is, observed counts are compared to expected counts. Obtain the expected frequencies defined as Eij is equal to row total times column total over grand total. Compute lambda square is equal to summation of 0ij minus Eij squared over Eij. 0ij is the observed frequency in the ij cell of the contingency table. For a 2 by 2 contingency table, such as it is illustrated below, the chi-square test statistic can be obtained as lambda square is equal to n into bracket ad minus bc squared over a plus b into bracket c plus d into bracket a plus c into bracket b plus d. Evaluate the p-value. Decision: reject, not reject. Limitations. Some of the limitations of chi-square test statistic include: it does not give much information about the strength of the relationship or its substantive significance in the population. It is sensitive to sample size, that is, the size of the calculated chi-square is directly proportional to the size of the sample, independent of the strength of the relationship between the variables. Also, it is sensitive to small expected frequency in one or more of the cells in the table. Summary of study section 7. In this study section, you have learned that the procedure by which we reach a conclusion about a population on the basis of the information contained in a sample drawn from that population is regarded as inferential statistics. Statistical inferences procedure are employed to draw inference about the population. Depending on the research objective, we can classify statistical inferences in two categories, namely estimation and hypothesis testing. Estimation is a form of inferential statistics in which a researcher wants to estimate the value of a parameter, e.g., the response rate of a leukemia investigative drug. Hypothesis testing is another form of statistical inference where we want to compare the parameters for two subpopulations using statistical tests of significance, e.g., testing whether men have higher cholesterol level on average than women. Student t-test, simply called t-test, is a parametric test statistic used to compare the difference between population mean value when sigma, population standard deviation, is unknown. Chi-square test statistic is an inferential statistic technique designed to test for significant relationship between two categorical variables, usually organized in a contingency table. Now we've come to the end of study section 7. Thanks for listening.